Okay, this is our Chapter 10 video. This chapter is called Thermochemistry and really is all about energy. It's the energy changes in chemical reactions. And energy is a hugely important topic, whether you're talking chemistry, biology, physics, engineering, whatnot. It's super important. And the chapter has some advanced topics, and some are not even listed here, and even the last three here I'm just going to touch on briefly. So the majority of the video will be those first four topics. And the first thing I want to talk about is some terms that you get introduced to. And the first thing is state functions. What is a state function? A state function simply means that the state of a given substance, say some water in a beaker, is independent of how it got there. It doesn't matter if it started out as ice and melted or started out as boiling water and was cooled. All that matters is its current conditions, its current state. Okay? And that's somewhat obvious, and you might wonder why we worry about that. Well, an example of why we worry about it, because it ultimately means the path how it got there is irrelevant. So for instance, let's say we're interested in knowing the energy associated with A going to B. And let's say that's not measurable. It's not something we can measure, and that happens often. But let's say we do know the energy associated with A going to C, and we also know the energy associated with C going to B. Well, hence, we now know the energy associated with A going to B. It doesn't matter that we took a different path. The change in energy is the same. So altitude change is a state function. The difference in altitude between here and Clingman's Dome, the highest peak in the Smokies, is independent of the path. But distance is not a state function because that is dependent on the path. You see? So it is nuanced, but somewhat understandable and important because that allows us to do some of the things later in the chapter, like Hess's law, to get to an answer that we're interested in about energy of a reaction when we can't directly measure it. We can take a different path, if you will. So that is state functions. And then the next thing, the first law of thermodynamics, you learn this back in probably literally middle school, but certainly high school. Energy is neither created nor destroyed. Another way of saying that, the total energy of the universe is constant. So if it looks like energy is being lost, that's simply it's being giving off to the surroundings. It's changing form, okay, and moving. And heat is just, transfer of energy in motion. And the universe is made up of the system and the surroundings. And the system is pretty much what you're interested in measuring. And you can define that lots of different ways. And it's important that you define it because in order to measure any heat that's lost or gained by the system, you have to know what the surroundings are and be able to measure those, or you might miss it, if you will. So the system can be defined as just the reacting molecules in your reaction, or it can be the reacting molecules and the solvent that they're in, or it can be the reacting molecules, the solvent, and the chamber. So it's important that you define that. Now, as we said, energy is neither created nor destroyed. Our systems can be vastly different. We can have galaxies, we can have a beaker. But heat can be lost or gained by those systems, as can work. Now, your book talks a lot about work, but I am not actually going to really talk about work. Just read a little bit on it, realize it's there, but we're going to simplify the chapter and basically kind of focus on only the heat, because the total energy of a system is a combination of the work and the heat. And we're kind of going to look at systems in which work's not really being done on it or it's not doing work. So we can't talk about combustion engines because those are doing work, right? The gases are produced, they're expanding, the pistons are being moved right in the cylinders. That's doing work. Okay? But there's lots of systems in which we can just define the energy associated with a chemical reaction. Reactions in our cells, reactions in the environment, all sorts of things, right? So when we define our system, there's different ways of thinking about it. There's what we call a completely isolated system where no heat is lost. Now, that's only theoretical. Even in the lab, you can have a super thermal box or something like that. It's still going to lose heat or gain heat over time. But if it's slow enough, we consider it pretty much an isolated system. Now, I've drawn this little line here because this is not very clear. This is actually got a lid on it. So this is a closed system. Heat, energy is exchanged, but nothing else. Or an open system, you can have matter and all sorts of stuff exchange. Water molecules are actually lost. In this system, the water molecules will condense and stay in there. So that's isolated, closed, and open system. Now we can define some other terms, exothermic and endothermic. Exothermic is just what the root of the word is, exoskeleton, something like that, exterior, outside, given off, if you will. Energy flows out of the system. The convention is negative sign. And that is Q, which is heat. And heat is just energy in motion, right? Exothermic, negative sign. Endothermic, positive sign. Energy is coming into the system. Q is going to be positive. Energy is released. It's going to be negative. Now we'll go ahead and define enthalpy, another term, and it's on my outline for the video. And enthalpy really is simple in the sense that it's just heat, energy, same thing as here, only at constant pressure. And that's nice because now we can't, once again, look at combustion engines, but reactions in cells of the body, for the most part, reactions in your body, with the exception of maybe your lungs where pressures are changing a lot, are at constant pressure. Reactions in the environment are pretty much at constant pressure if we're not dealing with some sort of storm event, whether it be a lake or the soil or the atmosphere, right? Chemical reactions in our laboratory, for the most part, are constant pressure, unless you're producing gases and it's a closed system. Then you would have a problem because the pressure would be increasing. But so many reactions are constant pressure, so that we just define basically heat at constant pressure is enthalpy. And it's the same sign convention. Exo is less than 0, endo is greater than 0. So one of the things we can talk about now is phase changes. Phase changes are when a substance goes through a change in phase, solid, liquid, gas, right? And a lot of people don't realize that temperature doesn't change during a phase change. So if I put a pot of water on my stove to boil it to make some pasta or something like that, it starts out and I add some heat and it warms up until it reaches the boiling point, which of course is 100 degrees Celsius or 212 degrees Fahrenheit. Once it reaches the boiling point, no matter how much heat I apply, the temperature does not increase. The energy goes into it, now boils the water faster, and the energy is going into breaking what we didn't talk about, chapter 6, the intermolecular forces holding the water molecules together. Not the bonds holding the oxygen to the hydrogen. Those are the intramolecular, within the molecule, not between the molecule. So the energy is going to breaking apart the water molecules, so they're now in the gassed phase and free from bonding intermolecular bonds. That's what the energy goes toward. If you don't believe me, do the study yourself. Get a thermometer, hold the thermometer in the water, and notice no matter how much you crank that heat, the temperature will not rise. Now, you might have experimental error which says it's slightly more or less than 100 or 212, and do not rest it on the metal pan because you'll get a false number also. But that's the case. It does not change. So what you see is here, energy added, change in temperature. No change in temperature here as I'm melting it. No change in temperature as I'm boiling it. You see, this is water going from minus 18, right? Starts at minus 18 here. It's going to go heat up. Then you'll see a change in temperature. Then it melts, no change in temperature. Then it heats up to the boiling point, no change in temperature. And then we can vaporize it, no change in temperature. And then you can heat that vapor even further once it's all vaporized. That's a heating curve. No change in temperature during phase changes. Okay? And we can use these equations now to actually calculate how much energy is needed. So heat capacity, Cp, we won't use this much because it's not defined per amount of substance. Energy required to raise the temperature of an object 1 degree C at constant pressure. It's not very useful because it doesn't account for the amount of the substance you have, which of course it takes more heat to boil a mill of water than it does a liter of water, right? Or to heat it, for that matter. It doesn't have to be boiled. So we don't use this much. We want to define it in terms of the amount of material, whether it be mass or moles. Okay? And that's what makes sense. And here you see substances, right? And there's water at 25 degrees C. There's its heat capacity in mass and in moles, in grams and in moles. So it just depends on the units. And it's per degree C. So it's the energy necessary to raise the temperature 1 degree C but only in this case, now we're defining it either per gram or per mole, which makes sense. Now you can compare substances. And when you see that, oh, metals are very low, obviously, that's why we make our pans out of them to cook, because they heat up quickly, right? It doesn't take much heat to get them to be hot, to cook in. You don't want something with a high heat capacity, because it takes forever to heat it. That's why it's cooler next to a body of water on a hot summer day, because the heat capacity of air is about 1/4 of what it is for water. So that temperature changes quick. So when it heats up on a hot summer day, it gets up to 90 degrees, 95 degrees in the air. The water's still, 65, 70 degrees. That has to do with the heat capacity. You can think of it as the heat capacity as the resistance to change in temperature when heat is applied. That's really what heat capacity is, right? And so the higher the number, the more resistant it is to change in temperature. So now you can actually do the calculations, and we'll do this in class, using different equations. Q equals mc delta T, that's the amount of substance, the specific heat capacity, and the change in temperature. So I can figure out how much energy is needed to raise the temperature of ice from minus 18 degrees C to 0 degrees C. All I need is the specific heat capacity of the ice, the mass of the ice, and then the initial temperature, and we'll be heating this up to 0 degrees C, so the change in temperature, delta T, will be 18 degrees C. And here you have, this is water at minus 10. We don't have minus 18, but you can use that because the heat capacity doesn't change that much for different temperatures of the ice. Here we saw that we can have different heats of vaporization. I kind of missed it. These are the heats of vaporization. Here, the heats of fusion for melting. We call that fusion. And you can do it at the normal boiling point, but you can also do it at other ones. You can do it at a different pressure, right? It's still constant pressure, but you can do it at a different pressure. And they change significantly, where these don't change as much, so we don't list those there. But we can use minus 18 degrees C here. We can use the minus 10, no problem. And then we would actually use this for the energy needed to just melt it. Now you notice there is no change in temperature term because there is no change in temperature. Just the amount of substance, in this case it's just moles instead of mass, and then the heat of fusion. And we'll do that in class. We'll do a calculation where we calculate how much heat is needed to melt ice that's at minus 18 degrees C. Now you can use the same approach to apply it to figuring out the heat capacity of a metal. Let's say I heat a metal up to 70 degrees C and then I drop it in some water. Well, the heat lost by that metal will warm the water, and ultimately the temperature of the water and the temperature of metal will be the same, the final temperature. And because we know the information about the water, its mass, its heat capacity, and all of that, and we're going to assume no heat is lost, all the heat lost by the metal goes into the water. We can figure out what Q is for the water. So you can do this calculation for water, knowing the amount of water, the heat capacity, and the change in temperature, and as long as you know the initial temperature of the water. Then do that equation again once you get Q, and you do it for the metal, and I'll put C of the metal, delta T. And now you have the Q because the heat lost equals the heat gain. You simply solve for the heat capacity of the metal now, knowing the mass of metal you used, the temperature you heated to, and the final temperature is the same. So the final temperature of the metal is actually lower, so that's why that negative sign is in there. I don't do it like this. I simply just use the equation twice and use a positive Q value and then just calculate it out. But this is the way most books show it. And they want you to realize the heat lost by the metal is gained by the water, so they are the same heat, just opposite signs. So that's pretty useful. We used to do a lab like using that. I'm not sure that we do anymore. So we can use calorimetry to determine heats, and we can do this in terms of heats of reactions, or we can do it for metals. This would be kind of a coffee cup calorimeter type of device, measuring the absorption of heat. That's all it is, calorimetry. So we can look at chemical reactions. Now we can do a specialized, and you'll do this if you take physical chemistry, You have a specialized calorimeter that's a little bit more elaborate than a coffee cup with an actual sealed system. And in order to use calorimeters, you have to first calculate the heat capacity of the entire system, okay, of that calorimeter. Once you do that with a known substance, then you can put substances in here, and this is how you can do like food calories. What are the calories associated with, the Snickers bar, things like that. You can burn these materials and measure the energy and use the same principle here to get the energy of the substance that you're interested in. So that's bomb calorimetry. The last thing I'm going to talk about here is Hess's law, because so I've got on my outline here. Enthalpies of reaction. So any reaction now, we can have heats associated with it. And this ties into Hess's law and calorimetry too. A plus B goes to C. We can have a delta H for that value in kilojoules or joules or whatever. It can be negative or positive. That's the energy associated with it. And it's specific for the amount of moles of substance. If I double it, well, this would double also. Obviously, you know that. If I burn twice as much fuel, I get twice as much heat out. So what I mentioned before, Hess's law is this idea that, hey, I don't know what the heat associated with A going to B is, but I know what A going to C is, and I know what C going to B is, so I can combine these two to actually figure out what the delta H of this reaction is. That's the whole idea of Hess's law, is manipulating equations. Now, in some cases, you'll have a series of equations. You might need to reverse one of them to get the reaction you're interested in, or you might need to multiply it by a factor. So what we'll do in class is do some examples where we'll manipulate a series of reactions to get them to sum up to the reaction we're interested in to get our enthalpy, and that's because enthalpy is a state function. We can do that. And with that, that concludes my video. So be sure to look it over carefully and read your book and be ready for a lecture in class.